Los aquí presentes y los conectados a través de nuestro canal de YouTube. La Escuela de Ingeniería Metalúrgica de la UPC se está preparando para los desafíos que enfrenta nuestra industria cuando se requieren implementar demandas asociadas a la sustentabilidad. Estas demandas incluyen aspectos relacionados con el medio ambiente, la tecnología, inversión, regulación, infraestructura existente y economía, entre otros. En este contexto tenemos el placer de presentar a la doctora Sara Hornby, quien nos dará una conferencia titulada The Green Steel Revolution. Esta conferencia se presenta gracias a las sociedades IST y TMS en el marco de nuestro capítulo estudiantil Materials Advantage, la Facultad de Ingeniería, la Escuela de Ingeniería Metalúrgica, INSITEMA y el Grupo de Materiales Siderúrgicos. La doctora Sara Hornby es descrita como una pionera, una líder rebelde, una inspiración para las mujeres ambiciosas. Ha demostrado continuamente que nada está fuera del alcance de las mujeres en la ingeniería. Fue la primera mujer en graduarse de la Universidad de Sheffield Hallam con honores en ingeniería metalúrgica y un doctorado en metalurgia industrial. Y pasó los primeros años de su carrera en Reino Unido trabajando para diferentes empresas. Sus funciones iniciales en Canadá y Estados Unidos, desarrollando nuevas tecnologías y aportando las mejores técnicas disponibles en la industria metalúrgica, mientras gestionaba miembros de equipo multidisciplinario en múltiples ubicaciones, junto con otros procesos de optimización y la fabricación de acero en orden arco eléctrico, la colocaron en una buena posición para establecer su propia empresa, Global Strategic Solutions, que proporciona consultoría experta y peritajes a la industria metalúrgica y afines. Sara es inventora de 5 patentes y es autora de más de 133 artículos, seminarios y cursos internacionales. Es miembro del Instituto de Materiales, Minerales y Minería. Fue ganadora de la medalla al Premio Hatfield 2022. En 2020 recibió el Premio Benjamin Fearless y el Premio John Bell. En noviembre de 2023 fue galardonada con un doctorado honoris causa en Ingeniería por la Universidad de Sheffield Hallam, en reconocimiento por su destacada contribución a la industria siderúrgica internacional, y es el John Elliott Lecturer 2024, otorgado por la IST-FDMS. La conferencia será llevada a cabo en inglés. Después de la conferencia tendremos una sesión de preguntas y respuestas. Si es necesario, yo puedo hacer la traducción de las preguntas, pues haré todo lo posible que se formule por nuestra audiencia, tanto nuestra audiencia aquí presente como por los canales de YouTube. So, good morning, everyone. Present here and connected through our YouTube channel. The School of Metallurgical Engineering at the Universidad Pedagógica y Tecnológica de Colombia is preparing for the challenges that our industry is facing when demands associated with sustainability require to be implemented. Those demands include aspects related to the environment, technology, investment, regulation, existing infrastructure, and economy, among others. In this context, we have the pleasure to present Dr. Sara Hornby, which will give us a lecture called The Green Steel Revolution. This lecture is presented thanks to the AST-TMS societies in the framework of our students' chapter Materials Advantage, the Engineering Faculty, the School of Metallurgical Engineering, INSITEMA, and the Conference Materials Group. Dr. Sara Hornby, variously described as trailblazer and rebel leader, is an inspiration for ambitious women who continually proven nothing is out of reach for women in engineering. The first woman to graduate from Sheffield Hallam University with a Bachelor in Honors in Metallurgy and Ph.D. in Industrial Metallurgy. She spent her early career in the United Kingdom working for different companies. Her initial Canadian and US air liquid roles, developing new technologies and bringing best available technologies to the metals industry, whilst managing multidisciplinary, multi-location steel members, coupled with other electric arc furnace steelmaking optimization positions, put her in good stead to set up her own company, Global Strategic Solutions, which supplies expert consultancy and expert witness to the metals and related industries. Sara holds 5 patents and has authored over 133 international papers, seminars, and courses. She is fellow of the Institute of Materials, Minerals, and Mining, and was their 2022 Hatfield Medal and Prize winner. In 2020, she was the recipient of the Benjamin Fearless Award and the John Bell Award. In November 2023, was awarded with an honorary doctorate in engineering by the Sheffield Hallam University in recognition of her outstanding contribution in the international steel industry. And is the 2024 John Lecturer awarded by the AST-TMS. After the lecture, we will have a question and answer section. If required, I can translate questions that are formulated by our audience. Dr. Hornby, the audience is yours, please.
Thank you very much, and thank you for that kind introduction, ladies. Good morning, one and all. Thank you for attending the John F. Elliott Lecture, The Green Steel Revolution. If I talk too quickly, please let Lace know to tell me to slow down. So the John F. Elliott Lectureship was established in 1990 to honor Professor Elliott, who was a late lecturer at MIT, for his many significant pyro and chemical process metallurgy contributions. So also to acquaint students, engineers, and the public with chemical process metallurgy, its contributions, and the exciting opportunities that exist within the industry in the hope of inspiring pursuit of careers in this field. Back in 1972, in a Journal of Metallurgy paper, 100 Years of Progress in Process Metallurgy, he did say and prophesied that electricity will become more important as an energy source than it is now. But I doubt that he ever thought of CO2 or hydrogen moving forward. I'm honored to have been chosen as the 2024 Elliott Lecture. And just a fun fact for you all, considering process metallurgy or other industrial pursuits, I actually have spent over 50 years in the process metallurgy industry, and I failed my chemistry at A level, and a lot of us almost failed our chemical metallurgy when we were doing our first degrees. So anything is possible. So why a green steel revolution? My definition of green steel is net zero emission steelmaking using fossil-free energy sources. It's important moving forward that zero emissions iron making is crucial for our greenhouse gas mitigation, but currently we're not competitive with fossil-based fuel technology. We're currently missing this 1.5 magic number for the global warming target. As you can see from the chart down here on the right-hand side, I've plotted where we were at 2022, and it's way above the government plans and projections and the 2.0 and the 1.5 constraints. In fact, in 2022, we input 5 gigatons more than 2021, predominantly from the top right-hand side, the coal, oil, natural gas combustion, 34 gigatons of which was contributed by them. So why the green steel revolution? Back in 2015, there was a plan to convert 800-year-old carbon-based blast furnace BOF steelmaking to the electricity-based 60-year-old electric arc furnace technology with major changes to the modus operandi. Carbon-free electricity, which is not an issue, but hydrogen direct reduced iron and green carbon and consumables would be added to the mix. The current steelmaking and iron making processes are shown here. I'm not going to go through them all. The main point to look at is the bottom line here, where we have blast furnaces producing 2.2 tons of CO2 per ton of steel making. The smelt reduction reduces to a max of 168, direct reduction at 0.95, and of course, scrap recycling at 100% is only 0.38 tons. The right-hand disk here I showed because it's an AIST interactive module where you can go into the AIST.org and actually look at all the different areas of steel making from iron on down to the final product. Carbon dependence is both with the blast furnace and the EAF, and I'm not going through all of these calculations, but you can see on the left-hand side that CO or CO2 is prevalent throughout the blast furnace, especially because they use coke to support the burden in the blast furnace. That is why we have the 2.2 tons of CO2 per ton of steel. In terms of the EAF, we use carbon for foamy slag and chemical energy currently. Excuse me. Now, the foamy slag is very important because it reduces the arc noise. It foams the slag, and because of the foamy slag, we have a greater surface area to react with the metal, and that gives us much faster reactions and allows us to increase productivity. However, when we have the zero carbon hydrogen DRI, we are going to be challenging the reactions needed, which are shown in the chart there. So the CO2 equivalent sources are shown on the right-hand side, lower table, and my pointer's not working, sorry. But basically, the blast furnace is the largest on its own, 1.2 tons of CO2 per ton. The second is the coke at 0.79, and the third is the EAF that drops down to 0.24. Now, the Paris Accord demands that we drop to 0.2 tons of CO2 per ton of steel by 2050. And currently, the average across the world is about 1.7. Now, the chart in the middle shows 10 million tons or more of steel produced by country, and also broken down by blast furnace BOF, which is the red bars, and green is the EAF. The black line is the tonnage. As you can see, China is producing almost 54% of the world's steel, which was at 57 in 2021, and it's currently dropping again. But 90% of their production is from blast furnace BOF steelmaking, and they use less than 5% during that production cycle. That has given them this 28% of CO2 for the world global emissions. Amazingly, the US is half of that, and yet we have 73% of EAF steelmaking. And just as a fun fact, excuse me, the Canadian wildfires that occurred in 2023 actually contributed 647 million tons of CO2 to the atmosphere, which is fourth only to China, India, and the US in terms of emissions. So the IEA, the International Energy Authority's 2070 vision, was actually conversion to 95% hydrogen DRI EAF steelmaking. Now, this is technically feasible. However, it's fraught with challenges, and I've enumerated 10 in the next few slides. The challenges and the exorbitant costs are driving new technology R&D as well. So I've looked at a few with a technology readiness level of between 3 and 7, some of which have occurred in the last 3 years. This is the most exciting era since the 60s, when we had continuous casting development and commercialization. So the first challenge that I've put forward is build rates, which I believe are unreachable. We're predicated on needing green hydrogen, energy, carbon, and better qualified or quantified scrap. From 1970 until 2020, the average DRI production was 2 million tons a year. By 2050, the IEA is predicting that we need this conversion, which will mean 411 million tons of DRI per year, of which 213 million will be hydrogen DRI. That hydrogen requirement would therefore be 11.5 million tons per year. We would need 692 terawatts to produce it through 1,240 20-megawatt PEMs. And the requirement for EAFs would be 810. Additional to that, because of the zero carbon DRI, we would need another 370 terawatts to melt even 80% zero carbon DRI with 20% scrap. There's other issues as well, which is the supply chains. At the moment, the deliveries for transformers are 106 weeks, and the costs in some cases have increased 85% post-COVID. So challenge number 2 is sourcing the green hydrogen. It's expensive and it's currently inadequate in terms of supply, seriously inadequate. Now, Lindy's little chart on the right-hand side, shows that we will need 252 tons a day of hydrogen, 592 megawatts of renewable energy for a blast furnace EAF reheat scenario for only 1 million tons of steel. So 2022, we only put on 0.11 million tons of green hydrogen. And in 2021, that was, 44% higher than 2021. In December of 2023, there were 45 million tons per year of hydrogen projects announced to 2030. And that was going to cost $570 billion. And it will only be 1% of the requirement. The hydrogen map showed here shows you all of the world's low carbon hydrogen, whether it's blue or green, projects throughout the world. And in 2023, there were 1,040 projects, of which there were $110 billion worth of projects in the front end engineering and design, and only 25% were past the financial investment decision process. There are a couple of blue hydrogen projects here out in Asia. Another issue we have is production efficiency for the hydrogen. It technically takes only 39.4 kilowatts per kilogram of green hydrogen to produce it. However, currently the processes are varying between 50 and 65 kilowatts. There is a new plasmolysis process where they're extracting hydrogen from waste, water, and manure. And they reckon that they can produce hydrogen with 8 kilowatts per kilogram, which would be fantastic for the industry. The other issue is the electrolyzer capex. Currently, it's at up to $1,750 per kilowatt. And the promise for the 2030 years is a target of 300 to 500 kilowatts, which looks as though it's impossible to reach. Third challenge is sourcing the renewable energy. On the right-hand side here, this chart comes from the Global Energy Monitor, and it shows the renewable energy by source. We need 1,437 terawatts by 2050, and that will be a $2 trillion investment. We currently, as a steel industry, use 8% of the world energy, and the production creates anywhere from 0.3 to 1 kilogram of CO2 per kilowatt, which is why the renewable energy is so important. So we have not enough at the right price. We need half or 50% reduction in cost. In 2022, the renewable energy only consisted of 29% of the world energy, which was 1% higher than that in 2023. And as you can see from the bottom right, excuse me, China is almost 3 times more renewable energy than the United States, which is the second largest. In 2023, we only added 0.5 terawatts of capacity throughout the world. And if you look at the efficiency level at 67%, 500 million tons of hydrogen would require almost 19% of the total world energy. So hydrogen also could be used for energy, but we're predicting only 2 to 3% will actually be used for an energy process. The one serious thing to consider that's been overlooked is the requirement for water moving forward in our green future. And it's predicted that we will be 30% lacking as we move forward. Green challenge number 5 is sourcing carbon. Historically, iron has been produced with renewables, but the 20th century saw electricity and coal, because of the deforestation, come to the fore. And then, excuse me, when energy became 20% of the OPEX, it forced minimization. And the numbers here in gigajoules are for the blast furnace BOF 18.8, arc furnace mills 4.3, and the DRI EAF steelmaking is 15.6. So you can see the advantage of the EAF mills from those numbers. Now, biomass use varies by world location, which is this top graph here. You can see that Brazil is the highest user, followed surprisingly by the United States. I had no idea how much we were using here. Excuse me. The cost of processing reduces world opportunities, however. And the other question is whether there's enough biomass close to use points matching our use weight rate requirements. As in terms of the blast furnace, we can only substitute a certain amount of coke for biomass in the blast furnace because we need the coke to sustain the charge that's put to the furnace, the lowest of which has been achieved by Kobe Steel with a record of 239 kilograms per ton of hot metal. Now, the arc furnace carbon replacement is possible, but it might be inefficient because with injection of carbon to date, 50% efficiency has been achieved on average, whereas using pig iron or DRI with carbon in situ gives us a 90%, 95% or more efficiency on the carbon molecules held within. Now, the fossil fuel co-injection is often needed with the biomass, which of course is not necessarily going to lower the footprint for the carbon. So I'm suggesting that we don't negate all of the carbon from the DRI, that we potentially run with 80% hydrogen, which would give us 1 to 1.5% of carbon still in the DRI. And I'll explain why that's important. The other issue, number 6, is sourcing scrap. 100% scrap renewable energy electric arc furnaces have the lowest emissions, no question. Most of the product quality is traced back to the melt shop and the quality of the scrap. And you can see from the right-hand side bottom that the obsolete scrap, the dark blue, is going to increase significantly to 2050. And with continuous recycling, the issue with the residuals, the copper especially, is going to increase significantly. The prime scrap is dwindling. There's going to be a dump of lower quality scrap potentially from China, which would be between 40 and 500 million tons in the next 10 to 20 years. And one of the big issues I have is that scrap is not sold, as would be ores, to exacting quality. So scrap dealers often mix good quality with really bad quality to get a mediocre quality and supply that. That needs to be changed, and we need to be able to buy to specific scrap qualities. Number 7 challenge is the zero carbon hydrogen DRI in the EAF. Zero carbon is inherent in 100% DRI, but 100% hydrogen use in the DRI plants. Currently, electric arc furnaces use about 45% chemical energy, and that's what the chart shows over here, with 23% of that energy coming from carbon oxidation. As I said earlier, carbon promotes the foamy slag, and it has other benefits because the CO bubbles that form stir and degas the melt, and they increase the heat transfer up to over 93%, increasing tons per hour and yield. Carbon in the DRI also reduces the FeO that's inherent in the DRI and also in the steel slag. It also has none of the ash volatiles associated with carbon that would be injected. The 1% carbon has been shown by ArcelorMittal in Montreal, that used to be Sidbeck Dosco, to give you up to 1.5% increase in productivity, up to 1.5 kilograms per ton reduction in electrode wear, up to 25 kilowatt hours per ton reduction in power requirements, and up to 1% increase in yield. Excuse me. So the zero carbon or inefficient carbon use is going to reduce the chemical energy, foamy slag, and its benefits, and it will lead to increased cost and lower productivity. There'll be more gang, more kilowatt hours, higher meltdown times, greater electrode and refractory wear, and it will use potentially twice the amount of biochar. And we'll get lower yields. There'll be higher temperature melting because with lower carbon, it will require higher temperatures. There'll be more FeO in the slag, excuse me, and the biomass will often need carbon for fuel injection, sometimes because of the nature of the biochar, but otherwise it's going to be a need because of the lack of biochar worldwide. We're going to have to redesign the electric arc furnaces and the refractories because there will be carbon dissolution from the current refractories that are used, and there'll be slag erosion. We're going to have a deeper bath because we'll need twice as much slag in order to create the reactions that are required. And that will require physical stirring of the bath to enable the interaction between the slag and the metal. And this will all be compounded by the dearth of DRI grade ores, which I will get to next. So the 8th challenge is sourcing DRI quality ores. Nominally only 3 to 4% per year of DRI quality ore is mined, and I'm talking about more than 67% iron. In 2021, 73.8% of the world ore came from Australia, Brazil, China, and India. The quality is deteriorating. Iron has dropped 2%. Silica and alumina, the gang, majority of the gang, has gone up 2%, and the phosphorus has gone up 0.02%. In case of the Australian ores, the Pilbara, it's very difficult to upgrade or extremely costly. So the thought process is that we will redirect the DRI that comes from the DRI plants. And those can process low-grade ores. That's not an issue. The issue comes when you try and put it through an electric arc furnace because of the volume of slag and the cost doing so. So the current thought process is low-grade ores to a DRI plant, and then it will go to a new melter, an electric, an ESF, basically, electroslag furnace. And from there, either the liquid goes to a BOF, which is obviously currently on site at the blast furnace, or it can be put into pig and fed to not only the EAF, but the blast furnace, or even liquid fed straight to the arc furnace. So there are some new technologies for low-grade ores also on the horizon. Electra has been able to process ores in excess of 30% iron at low temperatures, 60 degrees centigrade, and Nucor is interested in that. There's Calix in Australia. I actually saw the plant last week. They are producing DRI with hydrogen from fines, sort of flash oxidation, deoxidation. And Swinburne University in Australia with Cyro have produced a highly reducible flux lime pellet, which you can see from this bottom chart, allows the ore to be processed through only 4 steps instead of the usual 6. On the right bottom is a chart from Prime Metals that's showing the break-even point for moving from the smelter plus a BOF, which is the blue, to an EAF with high-grade ores, which is the grayish-brown. The top number is the top color, the lighter color is the transformation costs, and the darker colors are actually the cost for the EAF or the smelter. As you can see from their chart, they're saying 67.5% iron is the break-even point. So number 9 is the carbon capture and use or sequestration scenarios. The top right-hand chart shows you from the IEA.org data and statistics, the carbon capture installed by point source. And you can go into that system and you can choose how you look at the process. In fact, iron and steel production is the lowest of all that's there. And technically, the carbon capture or the CCUS is way below that required for net zero. Currently, it can technically assist with 54% of the hard to abate emissions. There are 35 global plants only that address 45 million tons of CO2, which is only 0.12 of the 36 gigatons that's produced every year. There are 200 new projects out there, but that will only add 0.6% to the capture. Relatively high conversion costs are associated with this because you need carbon-free hydrogen to chemically stabilize the CO2, and fixation is limited. And with regard to sequestration, it's geographically challenged. Not everywhere has the capability. For example, Japan can't sequester any CO2 in Japan. They have to send it offshore to the islands. They are slated moving forward as a catch-all solution for heavy industry, especially the blast furnace BOFs. But there's a quote from Sandbag here that says it doesn't make sense economically, environmentally, or energy speaking. The effectiveness and relevance varies widely across applications, and it could be appropriate for DRPs and relevant to iron and steel. But they're also saying that this might be worse for the industry in terms of reduction versus other alternative solutions. Now, Baotou Steel in China is going to put on the first commercial blast furnace CCS at the end of this year. It'll be 500,000 tons initially, but it will move to 2 million tons a year of capture. And they plan to use it for enhanced oil recovery or carbonated slag moving forward. Now, they're saying that the EU policies and funding are at the expense of other opportunities to decarbonize the industry. The other big question is whether the end users for the CO2 that's captured, the food, the chemical, and the enhanced oil recovery industries, whether they can use all that would be captured, or whether we need to find new users. I've always had a question as to whether we could capture the CO2 and reuse it back in the steel mills. I did a lot of work back in the late 80s, early 90s, where we actually used CO2 as a substitute for argon and nitrogen in the steel mills and reduced costs significantly. And it was not an oxidizer as originally thought. So the 10th and the final challenge I will go through is the conversion costs. The right-hand top chart shows you the projects that are currently being processed by the EU. There are 60 projects worth $92 billion, both CapEx and OpEx. The DRI cost doubles using green hydrogen via electrolysis versus natural gas, and the steel cost itself triples and will triple by 2030. We are already non-competitive, as you can see from the bottom right chart. If you look at hot rolled band, the USA currently is at 839, Western Europe at 680, world exports average at 580, but China's producing the same for $448 a ton. So it's necessary as we move forward to level border and import taxes on black steel for the non-compliant nations, those that are not attempting to reduce greenhouse gases. And as an example, the EU has their current tax at about $108 moving forward to 2030, and they will transition to what they're calling CBAM, which by 2050 will be $216 per ton. Projects are faltering, and it's primarily because the financial investment decisions are negative. They're not finding return on investment, so they're not putting up the money that they originally promised to the projects that are going on. And there's some examples here. ArcelorMittal in Gijon, that one's the French one, are still in the front-end engineering stage, and it's been delayed because of the cost of hydrogen, even though they were in a startup on natural gas. In Germany, they're waiting for government funding. ArcelorMittal Dofasco in Canada, they were supposed to have already broken ground for the DRI plant, but they are now 2 years behind because they have to run a 14-kilometer natural gas pipe to start them up. Algoma Steel has found that their costs increased from 0.7 to 0.875 billion. They've managed to de-risk 80% of the costs that they're expecting moving forward with pre-contracts, but they still have 20% at risk. The other issue, of course, to add to the costs is the conversion to blast furnace of blast furnace BOF steelmaking to EAFs is going to be the socioeconomic cost and the legacies that are left behind. And there's also going to be a continuing need for pig iron for the carbon moving forward in the EAFs. So one question becomes, can we look at blast furnace BOFs and revamp what's there to bring down the greenhouse gas emissions from them and bring it to parity with DRI EAFs? We look quickly at the new technology developments. Whilst the DRI hydrogen conversions have been looked at, there's been concurrent research, and they're honing in on carbon, electricity, and hydrogen as shown here. And basically, they're looking at biomass, CCS and CCUs, hydrogen reduction and production, and electricity. We're also looking at upscaling old non-steel or actually non-ferrous technologies to the ferrous side, the submerged arc furnaces, the open slag furnaces, and induction furnaces. But the challenges appear for all of them to be increased energy requirements, the scalability of the technology to meet blast furnace plant sizes, timeliness to market, and I'll show you a couple of examples, plus the Chinese techno-economic advantage that they have for hydrogen and green energy. So again, back to the best available technology and more applied research put to brownfields sites might be a better way to go as a stopgap between now and finding cheap hydrogen and renewable energy sources moving forward. One example of timely solutions, this chart was put out recently to show a 15-year development for the Finex fluidized bed process. But in actuality, if you look back to where it started, it was back in the 1940s, which means it's been 80 years in development. And it's still under research to focus on greater efficiency and less cost. The second example is Hysarna. That's a 38-year development of a cyclone converter over a smelt reduction furnace. One of the new technologies being looked at is this electric smelting furnace, ESF, which includes the submerged arc furnace and the open slag bath furnaces. They can take the lean ore and overcome the instability for the resulting DRI, low-grade DRI, which would not apply to an EAF melting situation. The top right-hand chart here shows that currently the maximum on the round ESFs is about 1.1 million tons a year, and for the square ones, it's 1.4. So they're looking to increase the tonnage potential from these furnaces. They also need to optimize the power intensity and look at sustainable renewable energy use. They also have to look at electrodes because currently they are carbon, which is not going to reduce carbon footprint. Integrating them into brownfield structure also needs to be looked at because it's going to be lower than the requirement for a replacement to the blast furnaces in most cases. So BlueScope, BHP, and Rio Tinto in Australia are all looking at the ESFs for this low-grade Pilbara ore that's available. But just as an aside, BlueScope is also relining their blast furnace, which will give them another 10 to 20 years. Fortescue, Prime Metals, and voestalpine are developing a prototype HYFOR process. It's a 900-degree centigrade fluidized bed. They currently have a 1 ton an hour pilot running it and have done since 2021. And they're going to put in a 6 ton an hour demonstration plant at Linz in Austria at voestalpine in 2027. Well, that's the plan, assuming that the FID comes through in 2024. It can process all types of ores, fines. It's modular, and the industrial HYFOR plus a smelter is an agreement with Fortescue that will produce liquid metal. There's also the POSCO fluidized bed Hyrex process, which uses hot hydrogen for ore reduction, and they'll put that to an ESF for DRI melting. And they are looking at a 300,000 ton a year demonstration plant for 2028. And they think they can commercialize that by 2030 for steel production. Biomass net zero iron making, biomass derived reductant resurgent to replace fossil fuels is not going to cause any problems in terms of retrofitting. Brazil, as I've said, has the largest biomass and iron ore production using 88% renewable energy, and they're using charcoal in their blast furnaces. Again, logistically and geographically, is this sustainable? Can we match the new bioreactors designs to the supply that's there? Do we need to do emissions life cycle analysis to ensure that the land use change from harvesting and producing charcoal is valuable versus potential crop use? And the other question is, can carbon neutrality be achieved? Now, Red Smelt in Brazil is saying that they can achieve net zero using a rotary hearth furnace and a smelt reductor to replace this submerged arc furnace. There's a new technology called ferrosilver. They're claiming that they can actually produce a sink of 0.845 tons of CO2 per ton of steel. Then they would be making green DRI from syngas that they will get from forestry and agricultural waste. They'll put biochar to the steel mill and they will capture the CO2 and they will produce new products such as fossil-free ship fuel and biomethanol. They're doing a pre-study currently for a 50,000 ton a year DRI plant, and they will put that at Ovako Steel in Sweden. And they're reckoning that they can do it for less than 0.9 terawatts of electricity per year and up to potentially 10.5 terawatts of biomass per year. The solid DRI process, Calyx I mentioned earlier, it's a flash reduction of fines down a vertical tube. It's multi-patented and it's been pilot tested in Bacchus Marsh in Victoria, Australia. They've developed this in 2.5 years, which is amazing, and they can process fines and waste materials. It's been proven to be able to produce green iron from the Pilbara ores up to 98% metallization, although some of the really bad ores are only down at 70-odd%. And they feel that they can do it with 1.3 megawatt hours per ton of HBI, and the cost would be a maximum of $520, and that's Australian dollars. So that would be 470-ish US dollars. It uses green hydrogen, but it's only in contact with the ore, not as a fuel. And they can produce from this zesty green iron a zesty steel, and the diagram is shown at the bottom. So they're going to take the hydrogen ore reduction, reduced iron, and they will put it to a continuous electric furnace with unpelletized lilac lime, which they also process, and they will scrub the excess CO2. And this potentially will give Australia a value-added DRI or HBI product to export versus the ores that they're currently doing. And as I said earlier, 36% of the world ore supply comes from Australia. The big surprise was the category of the solid DRI processes. The shaft furnaces from Midrex or from Tenova are shown at TRL 6 to 8. And I suspect that's because the hybrid hydrogen DRI EAF process that's been demonstrated is still a big question mark. And some of the open questions are, do we keep carbon in the DRI or not? And whether they can process the lean ores through to either an ESF or potentially an EAF. Now, the hybrid pilots produce 1 ton an hour of DRI, max of 5,000 tons per year. They've proven this lined rock storage for hydrogen, 100 cubic meters. However, for their 1.3 million ton a year plant that they're putting into Gällivare in Norway, they're going to need 120,000 cubic meters of storage, which is equivalent to 100 gigawatts and 3 to 4 days operation. The 1.3 million ton will go, demonstration plant will go into SSAB. However, we've just heard that this whole project has been potentially pushed out to 2040, and there's been no explanation as to why. So there's also a hydrogen rotary kiln that can be run on solar and wind renewable energy sources. There's a 0.5 ton an hour high iron DRI pilot in Germany that's been running since first quarter 23 on 14 megawatts of renewable energy. And the high iron has a joint venture with Hyron Steel in Namibia, and they're going to put in a 15,000 ton a year DRI plant with 20 megawatts of solar, and it's technically to start up at the end of this year. They will ultimately have a 2 million ton a year plant with 18 megawatts of extra wind power and 140 megawatts of solar power. And of course, we also need to look at CCUs, which could be suitable for taking the CO2 off these off natural gas run DRI plants, but that still has to be proven and upscaled. Electrolytic iron making is another option. The electrowinning can be at high or low temperatures. Basically, the redox reaction is the FEX or Y going to iron at the cathode and oxygen at the anode, and the ores, oxide anions, are actually the reducing agent. It's technically higher efficiency because the renewable energy is in direct contact with the iron. Now, the high temperature process, you dissolve the ores in the molten electrolyte to produce the liquid iron. It has faster kinetics, but it has very high capex and opex. ArcelorMittal et al. Explored this in the Medeo Ulcos process from 2004 to 2012, but it was never adopted. The low temperature is a solid iron process. It's got slower reaction rates and lower reduced renewable energy use with a lower capex and opex, as you would expect. ArcelorMittal Siderwin is a demonstration project at 110 degrees centigrade. It's an aqueous process for batch production of iron plates. Boston Metals is our infamous United States process. It's high temp. It's up to 2000 degrees centigrade. It's an MIT spin-off. It can process a wide range of ores, but it's limited productivity per cell due to current density and Faraday's law. But they have some critical factors to overcome. They need to figure out how to recarburize the iron. They have an anode question of longevity and an actual material, because currently they're running with carbon. They think they can run with ferroniobium, but it's not been proven yet. And the other issue is scaling. They will have to scale 8 times to go to demonstration and then 240 times more to go to commercial. The other issue they've got is cell voltage. They need to be down at 5 volts to run the cells to be economically viable, and they're currently at 20. And the question would also be existing brownfield site compatibility. Now, the right-hand side bottom picture is actually an aluminum plant in China, but these are equivalent to the cells that would be required to produce the iron. And they're currently saying that 400 cells will be required to produce 500,000 tons of steel. So if you're replacing 5 million tons of steel at the EAF, at the blast furnace BOF shop, you're looking at 4,000 cells being put in place. The other issue is that the aluminum process hasn't been automated for over 100 years of service, so it's going to take a lot of manpower to run this, which wouldn't be a problem for a blast furnace shop. Now, they've had a lot of DOE funding, $280 million to pilot, and $50 million current grant to produce ultra-pure chrome, metal, and high-temperature alloys at Weirton. They believe that they can be commercial for steel by 2026, and they're currently processing mine waste down in Brazil and producing chrome, manganese, and niobium from the process down there, which started this year. The cold side, Electra in Texas, of unknown capacity. backed by Bill Gates and Amazon, is less than 3.5 years old. It's low temperature, it processes using renewable energies, and it's converting ores less than 55% iron up to over 99% iron via electrochemical and hydrometallurgical processes. It's creating a 1 meter square, but we don't know how thick plate, which is going to be put to an EAF. It's modular, and they believe that they can reduce the CO2 by 90%. The other low and high temperature processes are off-spins from the Olcos research that was done back in the 80s and 90s. Siderwin, I've already mentioned, ArcelorMittal. They believe 87% reduction in CO2 is possible with a reduction of 31% in direct energy use. There's an Alcoin process, which is also ArcelorMittal is looking at as a low temperature direct alkaline electrolysis of ore. And this alcolysis, which is a high temperature electrolysis like Boston Metals. Plasma iron making is starting to raise its head again. This was around late 80s, early 90s, and basically failed because it was overpriced back then. It does have the advantage of producing very energetic exothermic hydrogen species, which overcome the endothermic nature of hydrogen, which is an issue in some processes, and it enables efficient redox chemical reactions. It has enhanced kinetics and energy savings potentially and lower reaction temperature. And there is a pre-pilot demonstration in the University of Leuven with voestalpine collaborating with them, called SuSteel. It's a single-step steelmaking process in an electric arc furnace or a melter. As I said, historically overpriced. We need to find lower capex and better reactor design for efficiency and low kilowatt hours per ton requirement, which was also a problem before. The refractory life needs to be improved, and ability to continuously produce needs to be designed. Now, there are some processes out there. There's the hydrogen plasma red, which is the European Research and Development. It's a reactor that's 100 kilogram scale. And if it works, it will then be pilot retrofitted to a direct current EAF furnace. There's an alumina bauxite, 180,000 ton a year plant turned into an iron making feedstock. And then, as I said earlier, this plasmalysis jet loop ammonia stripping from wastewater and manure is also a process that could potentially save the hydrogen world by producing hydrogen at 8 kilowatts per kilogram. So we look at potential brownfield decarbonization. Blast furnaces, we anticipate still needing 50% of the blast furnace steel making until 2050. So we're looking at best available technology. So the greatest decarbonization potential comes from the blast furnace side, and best available technology has already been shown to reduce CO2 by 25%. But we can also improve that further by improving measurements in the mills, because you can't control what you can't measure. We can intensify the use of metallics in the blast furnace, and I'll show you the BOF as well. And that would be either scrap or HBI. And the International Iron Metallics Association has shown that 8 tons an hour increase in productivity and a reduction of 7% coke can be gained for 10% metallization in the furnace. And Brooks et al. From Swindon University in Australia have shown that to be also fairly accurately true by the graph at the right-hand bottom. Biochar can be used for substitution for some coke and also for the pulverized coal injection to the tuyeres. We can also put in hydrogen or natural gas as tuyer injection. And for 115 kilograms of natural gas per ton of hot metal, the CO2 can be reduced 9% versus coke operation alone. Also, Hatch has run some, calculations And they believe that post-combustion PCI, this pulverized coal injection, plus 35 kilograms of 900 degrees centigrade hydrogen would reduce the CO2 20%, increase the energy to the mill by 35%, and would reduce the coke by 100 kilograms. But it would cost a lot, so you need to be careful. But if you add top gas recycling and CCUs to the top of the blast furnace, you can produce an 80% reduction in CO2, which would bring it down to about 0.4 tons of CO2 per ton of liquid steel, which is almost as low as the EAF. Another way to save is using blast furnace pellets versus sinter, which will give you an 85% less CO2 generation. And the Japanese Course 50 program has proven already you can get a 30% reduction in CO2 using hydrogen, coke oven gas, and CCUs on a 12 cubic meter diameter blast furnace, which is small. Their aim is to produce 50% reduction in CO2 with blast furnace DRI and hydrogen use. And again, Kobe Steel has the record for 239 kilograms of coke per ton of liquid steel using actually the HBI in the blast furnace. In terms of the BOF, increased scrap use as a coolant would be a way of reducing the CO2 and also increasing productivity. Currently, the world average of scrap use is 17%. The US is using between 20 and 25, but in actuality, in the past, we've used up to 50%. Now, there's a Swinburne program that was built on plant data, and those are the two graphs on the right-hand side. The top one shows increasing scrap reduces heat loss. So if you move the scrap to 35%, your heat loss is only going to be about 0.9. If you drop the scrap use back to about 10%, you're going to have a heat loss of 6.75-ish. This is going to require smaller scrap, probably preheated and continuously fed as opposed to a big bucket dump. Also, if you increase the post-combustion ratio from 10 to 30% on this bottom graph, then you're going to increase the scrap from 22 to 28%, this dotted line, and you're going to decrease the global warming potential following this red line by 10%. Also, HBI in the BOF is going to give you a greater cooling intensity and productivity versus scrap, as you can see from the chart at the bottom and the table. EAF, green energy, is the key, followed by the scrap quality. Renewable energy could have saved between 62 and 212 million tons of CO2 in 2023. And scrap melting at 100% with renewable energy will reduce the CO2 down to 0.18 tons of CO2 per ton of steel. This middle graph here shows the improvement from blast furnace BOF down to hybrid, which is the hydrogen DRI EAF melting. Any increase in what we call ore-based metallics, the DRI, HBI, or pig iron, is going to increase your amount of CO2 generation, as you can see, moving upwards. This is DRI EAF. This is DRI EAF with renewable energy. Scrap, and then scrap EAF with renewable energy. You need to beneficiate the scrap and maximize its use, obviously, because of that. And if we shred the scrap in-house by our own scrap shredder, we can improve the quality, the density, and increase the yield because you're cleaning the scrap, basically. And it's been seen that you can increase the yield from 89 to 98.5%. There's also the profit from selling the shredder fluff, as they call it, which is the non-ferrous that comes from shredding. Also need to have continuous analysis in the scrap plant to make sure of the quality of scrap that's going in the furnace. We need to develop residual insensitive steel grades or find a way of removing the residuals from the continuously recycled scrap. Another way to improve the arc furnace operation is to preheat the combustion air. And we've seen in the past that if you do that, you can reduce the kilowatt hours from 480 to 280, and you can reduce the meltdown time from 58 minutes to 42 minutes. Hydrogen substitution can be used fully or partially in the burners for the arc furnace. And one of my desires for every arc furnace operating is the use of a value in use model that will determine the scrap OBM mixes that are charged to the furnace to give you the lowest cost steel with the chemistry required. Also, off-gas analysis, which will reduce the heat loss to the off-gas system, which can be huge, as you can see, 36% of the heat going into the furnace. And also need EAF control to at least a level 2 minimum, if not 3. So the industry status, this is the map of the 60 key steel low carbon projects in Europe. I'm not going to go through them all, but basically the EU is leading because they have a dearth of natural gas, and their source is basically Russia, which they do not wish to partake in. They have significant funding from the governments in the European Union because of the carbon taxing that's been in place for many years. I love this map. This is the Global Energy Monitor.org's map of projects. And basically, you can get a lot of information from this, and you can play with it as you like. This map, as it's shown, shows 1,163 plants that are tracked. 185 are capacity reductions, 398 shown are capacity additions, and they show on the left-hand side by type of process. You can dial in. On the right-hand side, you can choose what process you want to look at, and then you can do it by the status at the bottom here: announced, construction, operating, mothballed, retired, canceled, operating, pre-retirement. These numbers and the circles, for example, I think the one I blew up was the number 12 here. If you hit these circles, you can blow it up as shown in the top right here, and it will show you what steel mills operating what type of technology are shown. So the red dots are integrated blast furnaces. The green dots are, I believe, the EAFs. The bluey brown ones are the blue ones are the oxygen furnaces, and the brown ones are the iron making. You can then go in and hit a button, whichever mill you want, and I've done the Soldana steel down here on the bottom, and it will tell you all about the steel plant, and then you can drill further down into the steel plant. And I've played with this map several times, and rather than show you all of the different options, I've summarized the global data here. The red are the integrated blast furnaces, and the purple are the integrated DRI plants, whether they're iron making or steel making. Basically, from 2 years ago to now, the number of blast furnace projects are almost identical to the number of DRI plants, whereas 2 or 3 years ago, DRI plant changes were going to be more significant than the blast furnaces. So obviously there's been a shift with the challenges to more blast furnace actual purchases and relines. The right-hand chart here just shows what Prime Metals is forecasting for the shift in steel production. It agrees with the IEAs. Basically, by 2050, we're going to be 2.2 billion tons of steel, but the blast furnace is going to drop from 1.35 to 0.75. And it's going to be replaced basically by the DRI melter, BOF, and scrap EAF systems. I'm not going to go through all of this, but basically there's a thought process out there that we look at in international solution of decoupling iron making from steel making. The global warming solution is going to vary by location, and that suggests this decoupling. For example, China has the renewable energy sources going currently. Germany's allocating money to Colombia for climate control and biodiversity efforts. Australia's got the ores, the renewable energy, and the investment potential. So perhaps we should look at doing iron making somewhere and then making steel elsewhere. Currently, the Middle East is able to make green steel without hydrogen at 0.25. Sorry, bird just killed itself on my window. 0.25 tons of CO2 per ton of steel. These are the committed green installations, or some of them, from 2022 through to 2029. I'm not going to go through the whole list, but it's there for you to look at later. So in summary, the scale of progress and investment falls way short of this 1.5 degrees C global warming potential. Hydrogen DRI EAF steelmaking is technically viable, but it's challenged by so many challenges, especially build rates and the greening of consumables, and additionally, the huge conversion costs. And it's kind of a catch-22 because the steel mills want a guarantee of low-cost carbon, energy, and hydrogen, and conversely, the people supplying want to have the demand and know there will be a demand for them to go ahead and produce it. The thought of decoupling iron and steel making, so you have iron and ore, the ore with the iron making and the renewable energy and steel making somewhere else. In the meantime, we need to look at black steel taxes for non-compliant nations, and we need to look at the best available technology and improve with AR&D at brownfield sites to make sure we've got a techno-economic stopgap in place. The green steel revolution has spawned innovation and new technologies, but the question remains, can innovation to market and build rates be sped up? Can CCUs be a true long-term fix for steel? And hydrogen production efficiency and cost be improved so that we can use them? So major career opportunities exist to further the green steel revolution, especially with out-of-the-box thinkers. So it's an exciting time to be in the industry. I thank you for your attention. And if you have any questions, I'd be more than willing to answer them. Thank you.
Dear Dr. Hornby, thank you very much for the presentation. I think you gave us a good spectrum of the current situation, the challenges that we are facing, the technologies that are arising in our current industry situation. So I think it gave us a very good perspective of what's going on in the green industry nowadays. So I will open now the question sessions, both to our auditorium and if the audience that is connected with the YouTube channel has some questions. I will translate that in Spanish. Bueno, muchísimas gracias a los que nos acompañaron. Creo que hemos visto un gran resumen en donde realizado por la doctora Hornby, donde nos muestra la situación actual a nivel mundial, los retos que debemos enfrentar, las tecnologías que se están desarrollando y la situación de la industria a nivel global. En el auditorio, ¿hay alguna pregunta que quieran formular en español o en inglés? Si es necesario, yo puedo traducir, o si en el canal de YouTube, en el chat, hay algunas personas que estén interesadas en formular alguna pregunta, con mucho gusto. No sé, ¿hay alguna pregunta desde nuestro auditorio? Por favor. In English or as you prefer, we will make a test. If you can hear our audience, please try.
Good morning.
Can you hear it?
No.
No? Microphone?
Good morning to Hornby.
No sé si estás escuchando. ¿Puedes hablar un poco más duro? Entonces,
Acércate, por favor.
acércate, por favor. Give us a second.
No, it's okay.
Sí.
Good morning, Dr. Hornby.
Good morning.
You mentioned the hydrogen production using wastewater. Could you give us some insight in that process and how it works?
No. You mean the one where they're producing the low kilowatt hours per kilogram hydrogen?
Yes.
The plasmalysis?
Yes.
From what I understand, they are just extracting the ammonia from the waste and from the byproducts from animals, and then they're separating the ammonia to hydrogen. Exactly how they're doing it, no, I don't know.
Any other question? So I also have a question that I saw for the solutions that in the blast furnace technology can be made. And you mentioned that if you replace pellets by sintering versus pellets, I understood that quite well, that you could save 85% of CO2 emissions. Did I got it right?
Yes.
And
why it's not 85% of the whole blast furnace, but it's pellets versus the sinter.
Okay.
If you use the sinter and then replace the sinter with the pellets, you'll reduce the CO2 from those pellets by 85%, not the whole blast furnace.
Okay, I understand.
Sorry. Yeah.
No, because I was wondering why, and now I understand. There is any other question from our audience or from the YouTube channel? I think from the YouTube channel audience, we don't have any question. And from our audience, also there is no any question in here in our auditorium. So I think anyway, we have your contact, and I think it was a very nice step in order to introduce us to this worldwide context of the green steel technology. So we are very, very thankful here in the School of Metallurgical Engineering. This is definitely a very important topic, and a topic where we want to work both in the academic and research areas, as well as in the with the collaboratory works with our industry. So what I have as a summary from this talk is that we have a lot to do. I mean, this is not yet defined, it's not yet mature, it's growing. So there is a lot of challenges that the new engineers will have to face, and we as a School of to contribute to this green solution.
Definitely. You know, I think the big shock came last week when it's not been announced fully in the news, but Europe was waiting for the hybrid plant to go ahead with this 1.3 million demonstration plant, and to have someone from Sweden that was connected find out on, I think it was Thursday, that the hybrid is now delayed till 2040 was quite a shock. And there's no explanation as to why, but potentially, I'm guessing, I don't think I made the point that the hydrogen pricing was promised at less than $2 per ton. And currently it's running anywhere from $4.50 to $10 US per ton. It's huge, and it's economically non-viable, which is why a lot of plants are starting up with natural gas as they move forward.
Yes, so there is then the context given in this situation of green steel, I mean, for making these new strategies available and feasible, economically speaking.
Correct,
Yes.
correct. In another presentation I have, ArcelorMittal and various other steel makers have mentioned billions of dollars to convert, firstly to renewable energy and then to the hydrogen scenario. I mean, it's huge numbers.
So,
But if anybody has any questions, please, contact me through the email that's there or connect with me on LinkedIn.
then, then thank you very much, Dr. Hornby, and thank you very much also for the John.
Could you also take a picture of the audience?
Definitely, we have it already taken. So,
Oh, okay, good. Thank you.
So,
Well, thank you for the opportunity to speak to the School of Metallurgical Engineering and the other people online. Much
Yes.
appreciated. And say if there's anything I can do to
No.
help, let me know.
Okay. So thank you very much to all the audience that it was connected with the YouTube channel and here present, and especially to you, Dr. Sara Hornby. So see you in the next time.
Okay, hope so. Thank you very much indeed. Bye-bye.
Bye-bye. Thank you very much. Gracias a todos.